So welcome back. So let's work in the case setup for this curve channel. So basically I already read the mesh here. So remember this is a 2D case. And let's go through the usual case setup. This should be fast. Okay, so this is an incompressible case, so no energy equation. We focus here. So we have here, and when you open here, the next correction that we want to look at is this one, curvature correction. So see that when you enable this, you get this coefficient here, okay? This can be user defined, okay? Can be any positive value. Usually 1 is okay, but it's up to you. So I will run right ahead. Okay, I will go right ahead and use it. And actually, let me check because I think I already have some output data here. No, I don't have output data. But okay, it doesn't matter. So okay, so let me disable first. So all the eddy viscosity models, we have this curvature correction as you see here. Okay, so let me run using this disable. Okay, so the case setup is just a periodic boundary condition. We impose here the mass flow and we get it working there. We get it the velocity evolution. So I'm not going through these boundary conditions. We have a few reports here, y plus average, maximum node, I computing here, mass flow, okay? So let me go, okay, I will initialize, okay, and I will show you now the beginning of the case, but I'm not going to run, even if it is expensive, you need to run like 2000 iterations because here, the mass flow, it needs to stabilize. So the mass flow stabilize very, very slow. When you monitor, you will see that it will have a very slow convergence rate. So it's like 2000, 3000 iterations, I don't recall. Okay, so numerics is standard. The only difference that we can set or disable that correction, okay? So if you press here, okay, see that nothing changed, okay? The fact that you enable or disable, nothing changed in your monitors and everything. Okay, so see that our case is running the usual way. And this is the important one that you need to monitor in this case. If you check the reference, okay, you will see that there is a mass flow there. Okay, so we need to get something similar, okay, to the reference value. See that you have a kind of a strange behavior at the beginning, negative, then positive, have this jump, and then see that it is approaching asymptotically to a value, but it will take a really long time, like 2000 iterations to get there. Our maximum CD viscosity ratio, many quantities we're monitoring, okay? But at this point, let me stop here because I already have a few solutions there. And let's open this. So NCC means no CC, no curvature correction, okay? So you have it there in your folders, and let me open the solution, okay? And plot the profiles, okay? So this is what you have, okay? So see that very nice mesh, it's well resolving. Let's see the here, 0.53. By the way, using this correction not necessarily needs to be well resolving, okay? So it can be well resolvable modeling with no problem. So what we're interested here is in plotting here in this line that we have in the middle. We want to plot the different quantities. So see that I compute these two custom fields, okay? Remember that you go here button and here you have it. So if you want to see how they were computed, here you have the functions. And in this case, let me plot, okay? So this is what we're getting with no curvature correction. And this is the validation data. Okay, so see that there is some difference here, okay? It's not as flat as in the other. No, we're not getting similar behavior. But let me write this solution, okay? So let me go and I can put it here, no CC. Okay, so we have that solution. Now let me go and open the other case with CC means curvature correction. Okay, so it's the same model, K omega SST. Remember that you have that one also for the parallel matters and K epsilon. Okay, it's the same idea. Okay, so if I go there, now again, let me plot that same figure. So see that clearly, you see the difference. And in this case, it is enabled using the default coefficient, okay, 1. Okay, I don't know why they call it constant, because you can change it. So again, let me go here, experimental data, and let me load the previous data, and see this one here. See the difference, okay? Our current data is the blue points, okay? And the original one, the previous no curvature correction, it is the red one. Sorry, the black points is the current one. That see that we have a very good match, okay, with the experimental out to this area. Then there are some differences, but as you go and change your coefficient, you might get closer to that one. So let's see, let me go here and change that coefficient to 10, okay? Let me run a couple of hundred iterations, okay? So see that here, almost 3,000 iterations it was running. Okay, so at this point I see that, okay, mass flow is still changing, but not that much. Okay, that modification added some, it had some effect here. Okay, but at this point I can say 10 to the minus 3, it is okay. So let me stop there and let's again compare. And see 10, okay, obviously this solution is not well converged, okay, I still need to make it converge better, but see that clearly a very different behavior, okay? So this is the idea of the curvature correction. As I mentioned, it's advisable to use the recommended coefficient, but you can change that coefficient, okay? By no means is one, okay? So now let me compare with the Reynolds stress model, okay, RSM. And what is interesting that, remember, the Reynolds stress model is an anisotropic model, so it doesn't suffer of these, let's say, limitations or deficiencies that you find in the eddy viscosity models that are isotropic. So see that there are no corrections here, okay, well, production or curvature correction in any of the formulations, okay? So here we have this value here, so let me plot, we have already the solution, so no need. And then also you have information for all the Reynolds stresses, but see here, no correction, and you can already see that you have this behavior, okay? Let me compare with the previous, no curvature correction, and voila, this is it, okay? So this is the idea of the curvature correction, and also see the influence of anisotropic models, okay? So actually, since that the Reynolds stress model is not that very good, at least the one that we were using, but there is an influence. But again, different models, different outcomes that you will see here, that for instance, using this one, the quadratic model, you will have this behavior, and the one with your salt is this one. Okay, so that's all for this case. Okay, at this point I invite you to play a little bit, and basically what you will need to do is to change, as you go for the k omega, change this value of the coefficient. So you want to see the influence, but I hope you got an idea. Okay, so that's all for the moment. Thank you very much for your attention. See you next video. Bye.